action not equivalent. But generally speaking, most of physics lives right here. So all three of them can be used equally well, right? So in classical mechanics, so you guys are already super familiar with this one probably, right? So these ones are more interesting, right? So the Lagrangian, so let's start with that one. So we define something which is action. So we have something that's kind of like kinetic energy, depending on what we're talking about. And we subtract something that's kind of like potential energy. So the question is like, what does this even represent, right? Because it doesn't seem to have any meaningful, like, I guess, meaning, right, to us. But, you know, we discovered in the math that you can do this weird thing. Basically, you can take this Lagrangian function, and usually this is a function of, and I'm going to use more traditional physics symbols, but you'll have position, you'll have velocity, which is the derivative of position, you'll have time, right? And you can do this weird thing, they figured this out, right? Where if you integrate this from some time to some other time, you get some value depending on the path you take through space, right? And so you can kind of visualize this as like, there's kind of this function that's everywhere in space that has certain values, and you can integrate along different paths. Maybe I'll use different colors to illustrate this. And you can get different values for this integral, right? We call that's specifically what action is. In fact, we can define it like that. So we say we take some Lagrangian and some path, right? And we basically have it defined as that integral that I showed above. And this is what action is right here. Now what's interesting is we showed that, okay, there's a bunch of different paths you could take through space. And this is not like normal space, because I might add, we have a weird thing called phase space because we also have velocity as a coordinate. But if you take a look at all the possible paths, and you end up trying to minimize this thing called action, meaning like you're going to get different integral values here. Like let's say this one is 5, and this other one is like 7. You're going to find one that will minimize this value such that if you were to change it just slightly in any direction, it would go up. In other words, it's a minimum, right? Or more like a stationary value, because technically it's not just a minimum. But so what we call this is the principle of least action. And what's interesting is particles in real life, like physics, they will follow these paths that minimize action. Let's say this 1, 5, for example, is the one that minimizes action under a certain field, right? Does anybody have any improvements to add as well? Because I know a lot of people are more experienced. So if you want to add comments, throw that in there.
Typically, when I see this written, they'd say S of X equals.
Yeah, they'll usually use the coordinate.
But you know what, though? In this thing that I'm trying to do a better job of following that guy, is so it's kind of sort of, I wouldn't even say it's mainly, well, it's kind of mainly X, but you have to also think about changing the Lagrangian too.
Yeah.
So I actually use notation in my last document of S as a function of X, and then I also, you know, to get like the independent variables to change, I found, because I did not follow the whole Wikipedia thing and stuff like that, so I find it useful to also say it's a functional of the domain of integration, which here is just an interval, right?
Right,
And you kind of take a variation over that too.
Yep.
Right.
Yeah,
So that's a good clarification. So a lot of times this will be notated like this, where X is actually a function over time, which says this is my position. And let's say this is actually a vector quantity, right? Like basically saying this is my path through space. So this is basically tracing out a path. The action takes a function and gives a value. We would call that a scalar. So we call a thing that takes in a function, gives you a scalar, a functional. So if you ever read about that, that's what that is. Okay, so the principle of least action says that the thing that minimizes the action is the actual path that a real thing will take through space, which is really interesting. And you can basically show that in this overlap here, things that are Newtonian, if you rephrase them with some thing like this, you'll end up getting the exact same path that you would traditionally. I'm not going to do an example, but if you want to, you can take like anything really simple, right? You can do like a ball falling in like a gravitational space, or like a pendulum or something like that. You'll get the same answer, right? So kind of interesting. You can take like orbits and stuff, right? And this even works in reference frames that Newton doesn't work for. That's why it was so useful. So you can do things like, for example, you can take a spinning reference frame, and Newton said that, well, centripetal force is not a real thing. It's fictitious, right? And if you use a non-inertial frame, you'll get wrong answers. Well, if you do Lagrangian mechanics there, you can actually still get the right answers, which is really weird. So it kind of has some sort of sturdiness to it that Newtonian mechanics doesn't have. So then Hamilton comes along and he reforms this. So there's something I want to introduce now, and it's called a Lagrange transformation.
You can probably erase the other word too if you want.
Oh, okay. I just wasn't sure.
transformation.
The lasagna.
The lasagna transformation, right? So what you do is you boil some noodles, and you make some ground beef, and then you layer them with it.
It transforms your food to lasagna.
Okay, so what is a Lagrange transformation? So there's a formal mathematics definition. I don't know if any of you care about this, but if you're curious.
The one that's kind of more well, the one with maxes or mins rather
Yeah.
and stuff like that.
Are you curious at all about that? I can throw that out
You know
there.
what?
I think that's useful.
Knew that some time ago, and I wouldn't mind a refresher on that.
Yeah, let's go for it. Okay, so there's a condition that has to be true in the formal mathematical case, the geometric case, that we don't normally care about. So be aware of that. Take this with a grain of salt, right? So we have to be dealing with a convex function as well as a convex set over which that function is defined. So let's start by...
So that means the Lagrangian doesn't have any of these weird things that we've been worried about for
Yeah.
the longest
Right.
times, right?
Right,
Yeah.
so it simplifies a lot of things. You'll see why it works. This actually works for things that don't have derivatives, and that's why it's nice. And so...
Oh yeah, right.
Yeah.
It just has to be continuous or something like that. Right?
Yeah, we'll take a look. So basically, we're going to start with the function f, defined from a convex set. So I'm going to put down here x is a
Oh, that's the set of
Convex
things. Okay, that's yeah.
set.
I was thinking of a different thing that had to be convex.
Well,
yeah.
I guess this could technically be a field, but we'll just say it's over the real numbers. It could be the
Mhm.
complex numbers. Could be whatever field you want to throw in there, right? But all right, so we've got a convex set. F is a convex function. I'm not going to formally define what that means, but there is a definition if you want to go look that up as well. I think it's a function.
It just basically means that you draw a secant line, right? And
Yeah.
Yeah.
It means the
It's-
secant line's always above the function.
secant line's always above the function.
And when you're talking in higher dimensions, you have hyperplanes, right?
Yeah, your
So-
secant
okay.
hyperplane is above.
Oh, okay,
Something
cool.
like that, right? So like maybe a simple intuition, right? This won't help you for all cases, but let's say you have like some sort of paraboloid, right? You can consider this concave or convex depending on like whether it's facing up or facing down somehow. And if you have a plane cutting through it, you can kind of take a look at what behavior it has anyway. That's a kind of good intuition to visualize when you're thinking about this. Okay, so what we're going to do is we're now going to define a new region in space. We're going to call it x star, and this is going to be